Hello everyone, welcome back to your Statistical Methods class. My name is Jessica Bray and I'll be your instructor for today's lecture. Now let's get started by reviewing what we covered last lecture. First, we practiced calculating R using this equation. R is equal to the mean of the cross product of the z-scores. There followed three steps. First, calculate the z-scores. Second, calculate the cross product of the z-scores. And third, find the mean of the cross products. This mean value was R, and R is the mean cross product of the z-scores. Next, we looked at what happens to means, standard deviations, z-scores, and correlations when we transform a variable. We transformed x by using addition. Specifically, we added 3 to each old x value to get new x values. Then we looked at what happened to the mean and standard deviation. If you add or subtract the same number to all values of the old variable, then the mean of the new variable is increased or decreased by that same number. But the standard deviation of the new variable doesn't change. To sum up, when a transformation involves addition or subtraction, the mean changes, but the standard deviation doesn't change. We also transformed y. To transform y, we used multiplication. Specifically, we multiplied each value of y by 2. Then we looked at what happened to the mean and standard deviation. We learned that if you multiply or divide all values of the old variable by the same number, the mean of the new variable is multiplied or divided by that same number, and the standard deviation of the new variable is also multiplied or divided by the same number. So, when a transformation involves multiplication or division, the mean changes and so does the standard deviation. Finally, we took the new x and y values and calculated the z-scores and correlation. What we found was kind of surprising. We got exactly the same numbers as when we used the old x and y values, even though we added 3 to all values of x and multiplied all values of y by 2. The z-scores and the correlation were totally unaffected. So we saw that if you transform the old variables by addition, subtraction, multiplication, or division, the z-scores and R stay the same. Dividing or multiplying by the same number usually won't change the correlation, except dividing or multiplying by a negative number reverses the sign of the correlation. For instance, multiplying by a negative number will turn a positive correlation into a negative correlation, or a negative correlation into a positive one. During the last lecture, we also learned that correlation does not imply causation. If x and y are two correlated variables, it's not necessarily true that x causes y or y causes x. Statisticians say that a correlation is spurious if x and y are correlated, but neither is the cause of each other. For instance, we talked about the very large and totally spurious correlation between annual cheese consumption and the number of deaths from tangled bed sheets. We also said that an experiment is a particular kind of study that is designed to discover whether a correlation between two variables is really causal. So now we're ready to go on to today's topics. But before we do, make sure to jot down any questions you might want to bring up during office hours. Today and for the next 3 lectures, we'll be covering regression, which is a method for making predictions about the value of a variable. Let's begin by discussing what we mean by the word prediction. In everyday speech, a prediction is an assertion about a future event. For instance, there are weather predictions on television every night. The weather forecaster predicts whether it'll rain tomorrow or what the temperature will be. In medicine, doctors want to predict whether a patient is going to get better. In business, manufacturers want to predict whether a particular new product is likely to sell. In psychology, we want to predict future behavior. For instance, whether a student is likely to do well in school. However, statisticians and scientists use the word prediction in a broader sense. They use the word prediction to refer to an assertion or guess about any uncertain event or fact, whether it occurs in the future, the present, or the past. For instance, suppose a student does very well in the statistics class. We might conclude that she has good math skills. This isn't a prediction about the past, it's a prediction about something in the present. So the way that statisticians and scientists use the word, a prediction can be about the past, present, or future. A prediction about the past is sometimes called a postdiction, but in this class we won't be using that word much. When I'm talking about a prediction concerning the past, I'll call it a prediction instead of a postdiction. Now, in case you're wondering how there can be a prediction about the past, I suggest you check out a really cool story on Blackboard called The Lady or the Tiger. It's set in an ancient kingdom. A king is angry with a young man and has him put into an arena with thousands of people watching. The young man stands in the arena facing two doors. Behind one door is a beautiful woman. If he opens the door, she'll become his wife. Behind the other door is a ravenous tiger. If the young man opens that door, the tiger will instantly jump on him and devour him. The young man has to choose one of the doors. And the story is about a prediction about the past. Which door did the young man open and what happened to him? I'll leave it to you to read the story and find out what happened. It's a great story and it's only about 4 pages long. Now that we're clear about what we mean by prediction, let's talk about how statisticians and scientists approach prediction. In statistics, prediction is nearly always about numbers. A common prediction problem in science is to estimate an individual score on some variable, which we usually call y. When you see a statistical formula with the letter y, the y usually represents something that's being predicted. There are many things a scientist might want to predict. A psychologist might want to predict how someone will perform on a language test. Or a health researcher might want to predict how well someone will perform in a sports event. The example we're going to use is a little less ambitious. We're going to talk about a young man named Waldo and try and predict his weight. Taking this example, take a second to jot down what you think y is. Here, y, the value we're trying to predict, is Waldo's weight. We'll discuss 3 strategies that we might use if we want to predict Waldo's weight. The first strategy is to use the group mean as an estimate of Waldo's weight. We'll start with this group information regarding men Waldo's age. Their mean weight is 170 pounds. That is, the mean of y is 170 pounds. The distribution of weight in men Waldo's age group is approximately normal. The mean here, again, is 170 pounds. Now the big question facing us is, where's Waldo? This distribution tells us a lot about the weights in Waldo's group, but we don't know where Waldo is in this distribution. A few individuals in this distribution weigh less than 100 pounds, and Waldo might be one of these skinny individuals. Similarly, a few individuals weigh more than 250 pounds. Waldo might also be one of them. Or he can weigh anywhere in between 100 and 250 pounds. So how do we figure out where Waldo is? Or put another way, how do we predict Waldo's weight if we have this group information? Here's how statisticians and scientists approach this problem. They think of it as sort of a guessing contest. Now take a second to jot down what guess you might make about Waldo's weight given this group information? If you want to have the best chance of being close to the correct answer, do you think you should guess that Waldo weighs 165 pounds or 105? Here's how a statistician sees it. The bars in the histogram that are close to 65 are very tall, indicating that a lot of individuals weigh close to that 165 pounds. On the other hand, there are not nearly as many individuals who weigh around 105 pounds. The bars around 105 are very low. So looking here, this bar here at 165 is much taller than the bar over here for 105 pounds. Waldo's weight may be close to 165, or it could be close to 105, or it might not be close to either. But if we have to choose between 165 and 105, there's a better chance that he's closer to 165 than 105, because there are more people close to 165 compared to 105. So statisticians would say if you have to choose between the two, choose 165. You stand a better chance of being close to his weight. Alright, let's suppose you have to choose between two guesses. You can guess that Waldo weighs somewhere between 100 and 150 pounds, or that he weighs somewhere between 150 and 200 pounds. What would the statistician tell you to guess? Here, the statistician would point out that in this group, there must be a lot more individuals between 150 and 200 pounds, compared to 100 and 150 pounds. So if you had to choose between one of these two guesses, the best guess and the one that's most likely to win is 150 to 200 pounds. Here's another one. If you can guess only one weight for Waldo, what would your best guess be? The statisticians would recommend that you choose the weight that has the most individuals near it. That is, you should choose the weight that has a lot of tall bars near it. The weight that has a lot of tall bars near it is here in the middle. It's the mean. The statisticians would say choose the mean weight, 170 pounds, because this is the weight that has the most individuals who are close to it. If you want to choose the correct answer, then your chances of being right are highest if you choose the mean. So now you understand strategy 1 as recommended by statisticians. If you know the group mean and you don't have any other information, then you should guess that Waldo's weight is near the mean. This is why strategy 1 is sometimes called playing the averages. Playing the averages gives us a good chance at being close to the truth. We're not guaranteed of being right if we guess the mean. Maybe Waldo actually weighs 250 pounds. But our chances of being correct or close to correct are highest if we guess the mean. Now, statisticians would say that the group mean is usually an excellent guess or an excellent estimate, unless we have information that will help us make a better guess. Now you might be wondering, what sort of information is it that will help us make a better guess? As we'll see, if we have a variable x that is correlated with y, then we can use information about x to make a better guess about y. We'll discuss two strategies that use information about x to make better guesses. One strategy is to use conditional means. The other strategy is to use regression. We'll begin with strategy 2, using conditional means. I'm calling it strategy 2 because the first strategy we discussed was using the group means as an estimate. We'll use the same example as before, where we have to predict Waldo's weight. Now, among men Waldo's age, height is correlated with weight. Weight is our y variable, because this is the variable we want to predict. Height is our x variable. It's correlated with our y variable and will help us predict y. Waldo is 76 inches tall. That is, his value on the x variable is 76. This scatter plot shows us the relationship of height with weight in a group of men Waldo's age. Each dot represents one man. The y variable, the variable on the y-axis, is weight. As I said earlier, the variable we want to predict is usually called y. And in a scatter plot like this, we use the y-axis to represent this variable. The x variable, the variable on the x-axis, is height. X is the variable that will help us make a prediction about y. As you can see, x and y are positively correlated. That is, there is a trend for the dots in the scatter plot to go up from left to right. The correlation here is about 0.75, so there's a very strong relationship between height and weight. So how can we go about answering the question, what is Waldo's weight? This line shows us the mean of y. In a scatter plot, this is one way we can show the mean of the y variable. It's a horizontal line drawn at the mean of y, which we know is 170. The line helps us to see which men are above the mean of y, these above the red line, and which men are below the mean of y, these dots below the red line. A few minutes ago, we discussed one strategy for guessing Waldo's weight. We can play the game of averages. That is, we can guess that Waldo's weight is equal to the mean of y, which is 170. But now we'll see how we can use another strategy, using the conditional means as estimates. Let's go ahead and describe what these conditional means are. Let's begin by focusing on this subgroup of men. These are men who are 65 inches tall. So these men are about 5 feet 5 inches tall. This circle shows the mean weight of the men in this subgroup. You can see that about half the men in the group have weights above the circle, and the other half have weights below the circle. The circle is in the middle, which is just what we'd expect for the mean. The mean weight of men in this subgroup is around 132 pounds. So we can sum up the information about this subgroup by using what is called a conditional statement. If height is equal to 65 inches, the mean of y equals 132 pounds. We call 132 the conditional mean for this subgroup. The if statement, which says if height equals 65, is called the condition. It tells us that the conditional mean is true only for men who are 65 inches tall. So we have one conditional mean. Now let's look at another. This time we'll focus on this subgroup of men. These are men who are 75 inches tall. So these guys are around 6 feet 3 inches tall. This circle shows the mean weight of this subgroup. The mean weight for this subgroup is 205 pounds. We can summarize this information. If height equals 75 inches, the mean of y is 205 pounds. So the conditional mean for this subgroup of men is 205 pounds. And this is the condition, if height is equal to 75. This tells us the circumstances, the conditions when the conditional mean is true. The mean is 205 only if we're talking about men who are 75 inches tall. So now we have two conditional means, and we can see that they're not the same, and they're not even really close. Let's do this one more time with this subgroup of men. These are men who are 76 inches tall. And here's the mean weight for men in this subgroup. The mean weight for men in this subgroup is 223 pounds. So if the height is 76 inches, the mean of y equals 223 pounds. The conditional mean is 223. The condition is if height is equal to 76. So the mean weight is 223 only if we're talking about men 76 inches tall. We've now calculated the conditional means for 3 subgroups, so you can see what conditional means are and how they're calculated. Now I'll just show you what the rest of the conditional means are. Here are the conditional means for each group. I calculated them earlier, and you can just take my word that they're accurate. Now we're ready to revisit our prediction question. What is a good estimate for Waldo's weight? Our strategy is to use the conditional mean to estimate Waldo's weight. And we saw this slide earlier. This slide told us that Waldo's height is 76 inches. We're going to use this information and our conditional means to make an estimate. Here are our conditional means. And these are the men who are 76 inches tall, just like Waldo. So if he's one of the men in this subgroup, we don't know exactly which one he is, but we do know that one of the dots in this red box is Waldo. The conditional mean for this subgroup is 223 pounds. Our strategy is to use this conditional mean as an estimate of Waldo's weight. So our estimate is that Waldo weighs 223 pounds. We don't need the other conditional means, so we'll get rid of them for a second. Now let's think of what we just did. We used the mean to calculate Waldo's weight, but we used the conditional mean just for the subgroup of men who are all Waldo's height. And this gives us a better estimate than if we use the mean for all men in the scatter plot. Let's go through why this might be. Here's the mean for all men in the entire scatter plot, 170 pounds. Now I'll introduce a new terminology. This mean is called the grand mean. It's the mean for everybody, not just a subgroup. We used to call it just the mean before because it was the only mean we had, but now we've introduced conditional means. So to help keep things straight, we'll call the mean for everybody the grand mean. Now by looking at the scatter plot, we can see why the conditional mean is a better estimate for Waldo's weight than the grand mean is. Waldo is one of the dots in the red box for men 76 inches tall. The conditional mean is right in the middle of these dots, so there's a good chance that Waldo is near the conditional mean. On the other hand, the grand mean is way below most of those dots. It's not very close to many dots at all. So we have a better chance of being close to the truth if we use the conditional mean to estimate Waldo's weight than if we use the grand mean. So now we've compared two strategies for making an estimate. We can use the grand mean, or we can use conditional means. And we've seen that a conditional mean usually gives us a better estimate for y. If we have another variable x that correlates with y, in our example, x was height, we used x to find conditional means for y, and those conditional means help to get a better estimate of Waldo's height. So now we're ready to talk about another strategy for making predictions. This strategy is called regression. There are other names for regression, like linear prediction. Linear prediction means predicting with a line. I like the name linear prediction better because it describes the underlying logic of the strategy. But in the course, we'll use the name regression because that's what it's usually called. As I'm about to show you, regression is very, very related to the strategy of using conditional means. For both strategies, you need a variable x that's correlated with y. Now here are the conditional means that we calculated earlier. As I'm sure you've noticed, the means follow a pattern. And here's that pattern drawn out. The conditional means follow a line. And this line has a very special name. This line is called the regression line. The regression line is a line that is intended to fit the conditional means. When I say fit, I mean the regression line is intended to be close to the conditional means. So now that we have the regression line, let's hide the conditional means and concentrate on the line. We'll now see how it can be used to predict Waldo's weight. As we learned earlier, Waldo is 76 inches tall. That is, his value on x is 76. We'll use that information to predict his weight with regression. Here's the regression line. And here's Waldo's height on the x-axis. X equals 76, where x is Waldo's height. We now identify the point on the regression line that's directly above 76. This is the prediction point. Its x-coordinate is 76. Now we find the y-coordinate of the prediction point. The y-coordinate is 219. So we say y predicted is 219. The little hat over the y tells us it's a prediction, or an estimate. This is our estimate for Waldo's weight. We estimate he weighs about 219 pounds. But remember, this is just an estimate or an educated guess. The scatter plot shows that among men 76 inches tall, some weigh less than 219 pounds and some weigh a lot more than that. Maybe Waldo is one of those men. But 219 pounds is our best estimate, our best guess, the number that's most likely to be close. So now let's go through the steps for making a prediction or estimate with regression. First, we find x on the x-axis. Second, find the prediction point on the regression line directly above x. Third, find the y-coordinate of that point. The y-coordinate is called y predicted. Fourth, y predicted is our estimate, or our prediction of y. I'll show you quickly on the scatter plot. First, we find x on the x-axis. Next, we find the prediction point. Third, find the y-coordinate of the prediction point. And fourth, this is y predicted for our estimate. So now here's a chance for you to try this yourself. Here's a little exercise. Let's say Israel is 65 inches tall. Use the regression line to estimate his weight. Here's the regression line you can use to do the exercise. And up here in the left corner is the problem. Israel is 65 inches tall. What is his estimated weight? Go ahead and take a few seconds to jot down your answer. Remember, you can get an answer by following the 4 steps. First, you find x for Israel on the x-axis. Here, x equals 65. That's his height. Next, you go up to find the prediction point on the regression line. Third, you find the prediction point's y-coordinate on the y-axis. The coordinate here is about 130, so y predicted equals 130. And y predicted is our estimate. Israel weighs about 130 pounds. Again, this is just an estimate. The scatter plot shows that some men who are 65 inches tall weigh only 100 pounds, and maybe Israel's one of those men. But 130 is our best guess, and the number that's most likely to be close to his true weight. Before we go on, I want to point out 3 small but important details. The first detail is a matter of terminology. As we've learned, this is the symbol for the predicted value of y. It's got a cute little hat on it. This hat is a mathematical symbol that indicates a number is an estimate or a prediction. Sometimes, but not very often, statisticians call this symbol y hat. But most of the time, this symbol is called y predicted or the predicted value of y. In this class, we'll almost always call it y predicted or the predicted value of y. Now for the second detail. When we draw the prediction point on the regression line, here are its 2 coordinates, the x and the predicted value of y. So this shows our prediction for Waldo. And up here is the prediction point. Its coordinates are 76 and 219. 76 is x, Waldo's height, and 219 is y predicted, Waldo's estimated weight. As another example, here's our prediction for Israel. The prediction point for Israel is down here. Its coordinates are 65 and 130, where 65 is x, Israel's height, and 130 is y predicted, Israel's predicted weight. Now for the third detail. For a particular value of x, the predicted value of y is usually very, very close to the conditional mean. Here's the regression line again for Waldo. If a man is 76 inches tall like Waldo, the predicted value of y is 219. We can see the prediction point on the regression line for men 76 inches tall. The y coordinate of this prediction point is 219. Keep that number in mind. Next, let's look at the conditional mean. The conditional mean for 76 inches tall is 223. With the regression line, we got 219. With the conditional mean, we get 223. 219 and 223 are pretty close to each other. Here I'm showing you the prediction point and the conditional mean at the same time. As you can see, the prediction point and conditional mean are very close to each other. As another example, here's the regression line for Israel. If a man is 65 inches tall like Israel, the predicted value of y is 130. We can see the prediction point for men 65 inches tall. The y coordinate of the prediction point is 130. Keep this number in mind. Next, let's take a look at the conditional means. The conditional mean for men 65 inches tall is 132. With the regression line, we got 130. With the conditional mean, we get 132. 130 and 132 are pretty close to each other. Here, we're showing 130 and 132 on the same slide. As you can see, the prediction point and conditional mean are so close they're practically the same. And this isn't a coincidence. Why isn't this a coincidence? Well, it isn't a coincidence because the regression line closely fits the conditional means of y. That's why it's so useful for prediction and estimation. The conditional means give good estimates and predictions. The regression line is close to those conditional means. So the regression line gives good estimates and predictions. Plus, there's something very, very nice about the regression line. It's a line. So, because it's a line, it has an equation. And the regression equation makes it easy to predict y. Before I show you about the equation, let me introduce a little more terminology. In regression, statisticians sometimes call y the criterion. Y or criterion are two names for the same thing. Y or criterion is the variable we want to predict. And in regression, statisticians sometimes call x the predictor. X and predictor are two names for the same thing. X, or the predictor, is the variable correlated with y that helps predict y. So now we're ready to discuss the equation of the regression line. Here's the regression line with the conditional means. But now we're going to concentrate on the line and its equation. And as you know, every line on a scatter plot has an unstandardized equation. And here's the equation for this specific line. The slope of the line is 8, and its y-intercept is -390. So now let's use this formula to make a prediction. Let's predict the weight of a man who's 75 inches tall. Here's the prediction point for men who are 75 inches tall. And we can see that the predicted value of y should be around 200, probably a little more than 200. Let's see what the regression equation tells us. Let's put the regression equation up here to make it easier. Y equals 8 times x minus 390. X is equal to 75, so we can plug in that number into the equation. A mathematician would say we're substituting 75 for x. So now we have 8 times 75 minus 390. So we substitute 600 in place of 8 times 75. Finally, we have 600 minus 390 is equal to 210. Now we can substitute 210 in place of 600 minus 390, and we have our answer. Y predicted is 210, and that's pretty much what we expected. We said the y-coordinate of the prediction point is about 200, maybe a little more. This time we'll try the equation with somebody we know, Israel. We're kind of cheating because we already know his predicted value of y is 130, but let's test out our equation. Here's Israel x value. X is equal to 65. And here's the regression equation. Now we do the algebra. X is equal to 65, so we substitute 65 for x in the formula. Our next step is multiplying 65 by 8, and that gives us 520. So we can substitute 520 for 8 times 65, and the next step is to subtract 390 from 520. And that gives us y is equal to 130, and that's what we were hoping for, because that's what we had already drew from the prediction point. Another nice feature about the regression line is that we don't have to use the scatter plot to find y predicted. We can rely on the regression equation. So here's a problem for you to do now. Let's say Sam is 72 inches tall. What would be his predicted weight? Here's the regression formula. Go ahead and take a minute to work through this problem. After working out this problem, you should get a predicted value for y of 186 pounds. Let's go through the algebra. The value of x is 72, so we plug that into our equation. Then we find out what 8 times 72 is. 8 times 72 is 576. We plug in that value of 576 and subtract 390 from it. That leaves us with the y predicted of 186. And we did this without a scatter plot. But just for fun, we can also estimate Sam's weight by using the scatter plot. And here's our regression line. Here, x is equal to 72, Sam's height. Here is the prediction point. Here's the y coordinate, 186, the predicted value of y. So now we're ready to end, but let me sum up what the main ideas were for today's lecture. The regression line is a line that closely fits the conditional means. Conditional means give good predictions. The regression line does too because it's close to the conditional means. One of the nicest things about the regression line is that it has an equation. And using the regression equation makes it easy to predict y. That's all we have for today's lecture, so make sure to jot down any questions that you may have to bring to office hours. Next time, we'll continue learning about regression.